Now this class is about the waves between parallel planes. Here we are discussing about TE waves. In the last class we have discussed about the propagation of TM waves between parallel planes. Now in this class we are going to discuss about the propagation of TE waves between parallel planes. A TE wave equation, as per equation 4 which was already discussed, can be combined to give an equation of the form dou square Ey by dou x square. This is a continuation of the last class, that is why the equation is numbered as 22, equal to minus gamma square plus omega square mu 1 epsilon 1 then epsilon y cap. And this equation holds good only for good dielectric between the plates. This equation is of the same form as equation 6 for the y component of magnetic field in TM wave case, and the solution for equation 22 is of this form. That is, this solution is somewhat similar to the solution that we have obtained in the case of TM wave. So just a slight difference. Here we are introducing A3 and A4. As for TM case, the two exponential x functions indicate two epsilon y field wave components traveling oppositely in the x direction as a result of reflection from parallel conducting planes. Now the above equation, we can write it in terms of sine and cosine as follows. Here we are introducing two arbitrary constants b3 and b4. In the last class we have introduced b1 and b2 for the case of TM wave. Since now we are discussing about TE wave, we are using another two arbitrary constants b3 and b4, and just as before, this also indicate a standing wave form of distribution in the x direction between the plates. Now we are using equation 4b to give the x component of magnetic field as equation 24. Now after performing differentiation, we are not showing the differentiation here. The above equation, that is equation 4c, which was discussed earlier, will give a form as given by equation 25. Thus the three field intensities for TE waves between parallel planes are determined. So if you want, you can skip this equation number 25. You can write up to equation 24, and then you can write the sentence that the three field intensities for TE waves between parallel planes are determined. Now, as already said, we assume that the plates are conducting. So the perfect conductivity of the planes require that tangential electric field, that is Ey, be 0 at the points x equal to a by 2 and x equal to minus a by 2. This condition will be satisfied with proper choice of angle involved, as this same equation we have seen in the case of TM wave, right? And that condition or the apt choice for angle involved is given by equation 26 and by assignment of either B3 or B4 as 0. The propagation constant gamma m in the case of TE transmission is determined as follows and is given by equation 27. This equation, as already said, it is similar to that for TM waves which we have already discussed. The conditions of propagation are the same, and the parallel planes become a high pass filter with cutoff frequency given by the expression equation 28, and the constants in the passband frequencies are given as gamma m, that is again equal to j b time. That expression we have already discussed in the case of TM wave and is given by equation 29, and the attenuation constant alpha m is found to be 0. So use of these relations developed above and the time and propagation function, by using those conditions we get the three equations, that is 30, 31 and 32, that represents the propagation of TM waves between parallel planes. And on applying these boundary conditions on this equation, we again get three possible conditions whose value depend on the value of m, and they are: if m equal to 0, then b4 will be 0 and odd fields are 0. If m is even, then b4 is 0. If m is odd, then b3 is 0. The configuration of the fields between the planes is seen as depend on the value of m. M is an integer, we all know it can have values m equal to 1, m equal to etc. And depending on the value of m, that is we will get various modes of designation. That is, for m equal to 1, for a TE wave it will be TE1, for m equal to 2 it will be TE2, etc. So once you study TM waves, then it will be the derivation of TE waves will be easy, because almost all formula will be the same and the pattern followed for the derivation will also be the same. There will be only slight differences. So once you study a derivation for a particular waveform, that is, if you study TM waves, it will be easy for you to derive the results for TE waves also. Okay, so thank you.